A very good morning to all of you. Today we are at lecture 26 of Control Engineering EI 503. What is the topic? Bode plot and inverse Bode plot. Numerical part 2. Actually, we have done already the numerical for the simple pole, simple zero, if there is type 0, type 1 and type 2 systems, right? But till now we didn't have that concept. We haven't had that kind of concept how there is a quadratic pole in nature, how it exists in the system, how to tackle it in the Bode plot. Okay, as well as we can actually do the reverse process if there's a Bode graph given. So how to find out the transfer function of the system, right? So that you can also do. So that's why this part has incorporated. So let's move on. What we have here topic, how to construct the magnitude plot for any specific problem and how to construct the phasor plot for any specific problem and how to conclude the stability of the system from Bode graph as well as the problem on inverse Bode plotting. Okay. So let's first take an example for the problem number 1 and let's have a look in this problem. Okay, what is suggest? What are the factors or the components of the Bode graph? Bode graph is given in this numerical that you have to observe minutely first before going to start the numerical. Okay, let's observe what are the basically what are the components is there. See 5, 1, 2. What is a component? Is a constant, right? S plus 3. So we have to take it in 1 plus S tau form, that means time constant form, right? 1 plus S tau form. And another issue is there. And this one is a simple zero. This is a constant gain factor. Then coming, it will be modified. And then we have here, it is type S to the power 1. It is referring type of system, right? And we have here the quadratic pole. What I have here, newly added quadratic pole. That we haven't done this kind of numericals in the previous class, right? So that's why I have incorporated. So we have identified so many components, constant, simple, zero. We have the quadratic pole as well as the pole at origin. That refers type 1 system, right? So what we have to do now, according to the step 1, we have to calculate what will be the basically the cutoff, what you can say the break frequencies, right? Or the corner frequencies, that is the corner frequencies. So how to calculate? Now we have to go for the time constant form. So what is the form? 1 plus S tau form, right? So it is the time constant form we have to make up. Now see, for GS, what we have here, so take 3 as common. So what do we get here? S plus S by 3 plus 1. So 1 plus S tau form. So we are getting here tau as 1/3, right? So what will be the corner, respective corner? That will be basically 3 rad per second. That is our number. That is our objective to find out the corner frequencies. That's why we are basically taking the basically the form that has taken, that is 1 plus S tau, that is called time constant form. What is called? Time constant form, right? So time constant form we are taking. So that's why 3 has taken. Similarly, we have here, see, you have to find here what is the formation actually. That will be equals to, we have here basically what is the form. Okay, in case of second order system, what we have? That was k omega n square by s square plus 2 zeta omega ns plus omega n square, right? Now if you normalize it, so what you get? You are dividing both numerator and denominator by omega n square. So what you get? K divided by s means you are putting here s equals to j omega as it is the steady state response, right? You are putting here minus j omega square means what? Minus omega square, it is coming divided by omega n square, right? Then we have for the second term, we have 2 j is coming over there as because j omega we are putting instead of s. So what we have here, omega n into omega divided by omega n square. And for the third term, what you are getting? You are getting basically omega n square divided by omega n square. We are getting omega, right? And now omega by omega n a whole square. That will be taken as the scaled omega by the natural frequency, that is omega by omega n square. What will you get? We will consider at u, right? So you are getting the u square. So omega by omega by omega n, we are regarding as u. That's called normalized frequency, right? So that's why what is the ultimate expression we are getting? Ultimate expression we are getting basically k divided by 1 is coming forward. So here 1 minus u square. That's the real part. That's the real part, right? Because we have to compute the, you have to look at the, what you can say, it is the magnitude part as well as the phasor part. So how to compute? There will be the real part as well as the imaginary part, A plus JB form, right? Then from where we can calculate the magnitude as well as the phase. That is our objective. That's why, that's our intention. That's why we are taking like this way. Okay, plus J2 omega, omega n 1, omega n cancel. So we are getting omega by omega. So we are getting 2 zeta. Zeta is missing over there. So right here zeta. So finally we are getting here J 2 zeta omega by omega n. That means what we are getting? That's a form. That's a phasor. Ultimately we are getting basically GJ omega, right? In the form of U. So it will helpful. It will very much helpful to calculate the magnitude. Now what is the magnitude? Magnitude part is coming. That is basically your k by root under 1 minus u square. Then we are going to have 4 zeta square u square. That's a standard form. Actually, we are going to use. Okay, and where omega by omega n, that is equals to u, is getting unity, then at omega equals to omega n, that was discussed in the earlier class, that was regarded as the corner frequency. What is regarded as the corner frequency? So in case of the quadratic pole in nature, the quadratic pole means what? Quadratic pole means what? Quadratic means basically there are two poles involved. So for each pole, two poles. For each pole contributing minus 20 dB per decade, right? And if the corner we are getting at omega equals to omega, let me take another color that will be easier to understand, right? So we are taking here pole having the contribution minus 20 dB per decade, right? Now it is for a single pole minus 20 dB per decade, right? Now if we are taking two poles into consideration, so what will be the slope? That slope contribution is minus 40 dB per decade. Slope contribution is minus 40 dB per decade. So for two poles we are getting minus 40 dB per decade. Before corner, it is contributing magnitude contribution by the pole before corner. Before corner, let me clear my sketch, then I am coming to that matter. So see, if the corner frequency we have recognized at omega equals to omega n, right? And at before corner, what is the contribution? Before omega n, the magnitude contribution of the quadratic whole part, that magnitude contribution is minus 40, 0 dB per decade. It's a big zero. 0 dB per decade, right? So it is coming as 0 dB per decade. So we are getting here 0 dB per decade, right? But after corner, that you have recognized corner as omega n. So after corner, the magnitude contribution is minus 40 dB per decade. That means if this is the fundamental things we know, so here we have to identify what is the corner. We have to identify what is the corner. That is an important issue, right? So we have to identify omega. That is the important main issue that we have to identify omega. Because then we can summarize regarding the magnitude contribution of that part, that is the quadratic part, that will provide 0 dB after before corner, and after corner it will provide minus 40 dB per decade. Okay, so this is the important aspect. And obviously, as we have derived, now just I am telling regarding that matter, what will be the phase contribution by this GT omega? What will be the phase contribution? If we are taking into consideration again the same expression, that is 1 minus u square is coming plus j 2 zeta u, right? That was our expression. So it is as a whole the expression for the what you can say the phasor. Now what is a phase part? What is a phase part? Phase part we are getting here. That will be again 0 and for this part what we are getting a plus jb form, right? So we are getting here tan inverse of b by a. As it is in denominator, so obviously it will come, basically it will come, that is minus tan inverse of b by a. Minus tan inverse of b by a. It is coming, right? So that's why we are getting here minus 2 zeta u divided by 1 minus u square, 59. So phi we are getting here, phi depends on is a function of zeta and obviously u. And what is u? U is omega by omega. So, so far the expressions we have to keep in mind. That is the thing we have to keep in mind. Number one, that is the magnitude contribution. Before corner, it is 0 dB. After corner, it is minus 40 dB per decade. So these two important issue that we have to keep in mind while we are dealing with the double, actually quadratic pole, right? Now in case of this, what is phi? What will be the phi? Phi having dependencies on zeta and omega n, right? So that's why that expression we have to keep in mind, the phi expression. What is phi expression? That is your minus tan inverse of tan inverse of tan inverse of 2 zeta omega by omega, and I'm putting just the raw value. Okay, omega by omega n divided by 1 minus omega by omega n square. That expression we will be using to calculate the phi for the contribution of this part, right? So these three important issues we have to keep in mind as we are talking about the quadratic pole. Okay, so let me clear my sketch. So here, as I have described, you have to identify now what is omega n. Okay, let's find what is omega n. See, if we are taking common 256, because our expression will be 1 minus u square plus j 2 zeta u, right? Now see here, that means actually what we are getting here, actually we are getting here 256. If you take common, we are getting s square divided by 256, or rather say 256, that will be your omega n square. So what is omega n? What you are getting? Omega n you are getting, that is 16 square. That means omega n square is 16 square. So you are getting basically omega n as 16 rad per second, right? So you are getting important information, that is omega n equals to 16 rad per second. Now, what you have to obtain? That is, you have to obtain zeta, as because you have identified omega n, right? So you have to obtain the zeta because you are going to use that I expression for having the dependencies on zeta as well as u. U means omega by omega n. As you already found omega n, so you need to find zeta. Now what is zeta? So you can compare with the standard second order quadratic expression that is 2 zeta by omega n s, that is becoming here 16 by 256, right? So as omega n we found 16, so just put the value. And what you get here, you will get here zeta may be calculated like this way, that is 0.5, right? So here omega n you have identified 16 rad per second, and zeta you have identified, you have calculated rather say, that is 0.5. That is that, right? So let me clear my sketch. So we have the important information now with us, that is your omega n 16 rad per second, right? And your zeta of the system, that is 0.5. And that will be utilized, this will be utilized to search the corner frequency by this quadratic pole, and this zeta will be utilized to calculate basically phase, okay, as well as omega n. So as it is a function of zeta and omega n that we have identified. Okay. Now see, let's move on. So what will be the steps? So on omega axis marks the point here at 6. Okay, from this point draw a line having the slope minus 20 particle. Rather to say, you may use these 3 steps. Fine. My advice is, that is written over the slide, fine. But my advice is just go through the parts where you are finding, this is basically simple pole, okay? So what is the corner you have identified? That is 1/3, right? That was the corner. That is basically 1 plus S tau. So S tau is basically 1/3, so we are getting the 3. So first corner you got, that is 3 rad per second, right? And that corner has contributed, that is written in my next slide, okay? That has contributed by the zero of the system. One and only single zero existing in the system. That zero is contributing 3 rad per second is the corner that formed by the zero, that component. And this is providing initial slope of minus 20 dB per decade that we have already gone through. And this part is providing basically the corner, that is the second corner of the system, as because it is 16 rad per second. 3 is the 3 rad per second is the first corner. It's coming as because you are plotting the omega, right, versus magnitude. So omega is starting from a quite small value to a large value, right? So that's why what is the initial frequency we need to consider? That initial frequency, according to our previous knowledge, we will put that will be the lower than the lowest corner. What will we put? The omega starting frequency, that will be lower than the lowest corner. What is the lowest corner in the system? 3 rad per second. So yes, we will start from less than 3 rad per second. That means we can start our graph from 1 rad per second. That will be easier sometimes. Okay, so it is 1 rad per second. We can consider. Now, so for the first component, so far we got 6 by S, right? So make a table for the magnitude plot, you make a table better to understand. Okay. So first component you got, that is basically 6 by S means j omega, right? So what is the component? Then what is the starting magnitude? Let's find, or starting magnitude or magnitude contribution by this component, right? And then find, sorry, before that, then find is there any corner, right? Corner frequency, and what is the magnitude contribution, that will come later on. Okay, that will be better. I think I have to clean up. So what you have here, we find here, first of all, then we have to estimate what is the corner frequency. Then we have to find out what will be the magnitude contribution by this component, right? Then we need to find out the net slope or net contribution, net slope. And in these regards, for the first component, we need to find out starting magnitude and starting frequency that we need to decide. Starting magnitude and starting frequency that we need to decide. What I said, starting magnitude, as well as starting frequency. Okay, because starting frequency, while we decide, then only we can calculate the starting magnitude, right, for the first one. So what we have here, the corner 6 by j omega, that is not contributing in corner. It is providing basically minus 20 degree per decade. Initially started with the slope that is minus 20 degree per decade, that we have already answered, right? So that's why it is providing basically no corner. What is no corner? It is basically no corner, providing no corner, right? And now you have to calculate what is the starting frequency. See, starting frequency will be the lower than the lowest frequency that we have decided. So what is the lower than lowest frequency we can choose? It is according to our choice. That is 1 rad per second. That's because you know first corner will arrive at 3 rad per second, right? So you can show your in your graph that it is appearing at 3 rad per second. So before that we need to start. Then we can plot the graph such that we can the corner can be visible, right? So in that case, corner will appear at 3 rad per second. That's why we are choosing the starting frequency, that is basically 1 rad per second, right? So if it is 1 rad per second, so what is ns? That is what is the starting magnitude. So let's calculate what is the starting magnitude. So your starting magnitude, right? That is your component you are taking 6 by j omega. So obviously the magnitude will be 6 by omega, and you are taking in dB. So what you get? 20 log of 6 by omega. That means you are getting 20 log 6 minus 20 log omega to the distance. That's why I have not written over there. So now your omega you have decided that should be 1 rad per second. That is the starting omega, right? So what you get here, 20 log 6 minus 20 log 1. So log 1 is 0. So you are getting basically 0. That is very much easier. So we are getting here 20 log of 6. That will be the starting magnitude. So put here in the chart, that is 20 log 6. You are getting a starting magnitude, that starting frequency 1 rad per second. Now what is the net slope contributed by this part? 6 by j omega. The net slope will be contributed by this part with no corner, right? With no corner. With no corner. So what is the net slope? Net slope is minus 20 degree per decade, right? So you are getting for the first one, first component, you are getting minus 20 degree per decade. Minus 20 degree. Let me clear my sketch. So for the first one, first component corner, then we have magnitude contribution by each part, then we have net slope calculation. Net slope, right? Net slope. So what you have here, component is your 6 by j omega, right? And here you are getting no corner. Then you have magnitude 20 log 6 you have computed. As because omega start you have thought that is 1 rad per second. Now what is the net slope? Net slope will be minus 20 degree per decade. That was done. For the first part we done. Now for the second one, let's extend the table and continue with the same concept. So for the second part, what is the next? A corner is coming, that is 3 rad per second. Keep it in mind. 3 rad per second. So obviously that component is nothing but your 0. of the system. So you are writing here 1 plus j omega by 6, 3, right? What is the corner? 3 rad per second. What is the magnitude? Magnitude contribution, rather say magnitude contribution, okay? That is basically slope is contributed by this part, that is 0 dB per decade before corner, before 3 rad per second, okay? And then you have next part is minus 20 dB per decade after 3 dB at 3 rad per second, right? After corner. These are these are concepts, right? That you are putting over there. And what is the initial slope was minus 20 dB per decade, so it is adding up, so 0 dB. So what will be the total summed up? So we are getting here again minus 20 dB per decade before 3 rad per second. And obviously minus 20 that will add up. Okay, so we are getting minus 40 dB per decade after corner. After corner, that means 3 rad per second, right? After corner, that means 3 rad per second, right? Now let's move on for the third part. That's very important and new to us, right? And that is nothing actually special, because you don't treat like this way. You know the corner is basically your omega equals to omega, y equals to unity, right? So omega you found here 16 rad per second, right? So here put the part that is your s square, that part, that means minus omega squared by 256 plus 16j omega by 256 plus unity. That what? Okay. J omega. So you are putting instead of s, you are putting j omega. That's why it is coming minus omega square. It is coming j omega. So what is the corner you found? Sorry, 16 rad per second. You found 16 rad per second, right? So what will be the net contribution, slope contribution first for this part only, that is 0 dB per decade before 16 rad per second, and minus 40 dB, keep in mind quadratic pole, there are two poles, okay, minus 40 dB per decade after corner. That was our theme. Now initially it has started with minus 40 plus 0, that means minus 40 dB per decade before 16 rad per second, and it will be minus 40 minus 40. So what will come? Minus 80 dB per decade. Sorry, 60 to 80, 80 dB per decade after corner. So it has, sorry, this one is the 0. There is a mistake. Please, that will be plus 20 dB per decade. Okay, so it was started with 0, sorry, minus 20 dB per decade, then it will be after 3 rad per second, it will be, sorry, minus 20 plus 20, it will come in, sorry, 0 dB per decade. Then after 0, it will start with 0 dB per decade, sorry, 0 dB per decade, and then it will end up to minus 40 dB per decade. Because see, it was 0, that was just mistaken. It was 0. So 0 is contributing 0 dB, and after corner it is contributing plus 20 dB. That was mistaken. Just make it correct. Okay. So it will be plus 20 dB per decade. So as it is plus 20 dB per decade, it is starting with minus 20 dB per decade, but it will end to 0 dB per decade after this corner. Then before this corner it was 0 dB per decade. Fine, it has repeated here 0 dB per decade. And then after corner it is contributing 40 dB itself, minus 40 dB as it is a pole. So minus 40 dB. That will be basically the table that will help you a lot to draw the graph. So what will be your probable sketch? Your probable sketch will be m in dB versus frequency. So you have the corners. Say suppose your corner you are starting with omega equals to 1. Your corner has 3 and having it another corner that is suppose 16. That is suppose 16, right? So what will be your graph? So your graph is starting with certain value of k, that is 20 log of 6, right? Certain 20 log 6, that is the height I am showing over there. So here it has started with minus s though, that is minus 20 dB per decade. Right? Then up to corner it is moving. After corner it is providing by a 0, that's why it will be 0 dB per decade. So it is horizontal line, 0 dB per decade. It will come till 16, right? After 16, it having the quadratic pole. So as it is quadratic pole, it is providing basically minus 40 dB per decade. So you are sketching here minus 40 dB, 40 dB per decade. So like this way it will continue. So minus 20 dB, 0 dB, minus 40 dB. We will just using different color, that will be minus 20 dB, then we have 0 dB, that's for horizontal, then we have minus 40 dB per this one. Okay, so these are the this is basically very simple one, but whenever you have to sketch, just you should draw the slope first. How to calculate slope? Initial point, and then you have to find out the final point. Okay, how to calculate the final point? Initial point you have calculated, that was in your chart, and in case of final point, what you have to find? You have to find the particular corner up to the corner. Suppose this slope will continue, right? You have drawn from starting from 1 to 10, you have drawn the slope, right? So it will not continue to 10, so it will end up to 3. So that's why farm line will be drawn up to 3, right? Then again from 3 to 16 there's a horizontal line, so you put a horizontal line, very simple. And then after that you have to draw the 40 degree per decade. So you are calculating where are you now? What is the magnitude? That is suppose m. Now minus 40. M minus 40. What is the level of m minus 40? Let's find. This is the level of m minus 40. Let's see. Okay. So this is you are getting minus 40 dB per decade. Per decade means what? You are starting with basically 16. So 16 to 160, right? So 160 is the omega. So that will intersect at a particular point. So you are mentioning that point, you are highlighting that point. And then this is your initial point, this is your final point. You are just putting a dotted line, that is the help line. But as there is no component in this basically particular problem, so you are making a form line that will continue till the end. Okay, that's the magnitude plot. Now in case of the phase plot, what will be the expression we are going to use? That is, this is contributing basically minus 90 degree. Only there is a single pole. We have done it. Huh? Then we have this expression. So that is contributing plus tan inverse of b by b. What is b? Basically omega by 3. Right? And a means basically 1. Now we have the lower half. So lower half is contributing minus tan inverse of 2 zeta u. U means omega by omega n by 1 minus u square. Omega by omega n whole square. So you are using that expression. You are using that expression to calculate basically the phase. That expression. And for what are the omegas you are choosing? You are choosing initial omega, all the corners, one octave below the corner, one octave above the corner. That are all the point of consideration you can take. Or you can choose any other points also. These are convention. And then 2 or 3 more points. You can calculate the absolute value of 5 by considering all those omegas. Just put out the chart and make it visible to draw basically the resultant pressure plot. Okay, so you are utilizing this one and this one for drawing the pressure plot. Okay. Now let's move on. What is the sketch? Let's see what you have drawn. See, starting with certain initial value, that is starting with point 0.1. I have suggested you to start from 1 because see, whenever you are starting from 1, then also you are basically you can observe this corner, right? So that's why my suggestion is start with 1 because there is no restriction, right? So that's why you can start with 1. So that's why here you are starting with that point and then you are drawing minus 20 particle that will come in up to 3, right? 3. Then there's a corner, then there's the horizontal line that we have already explained. 0 dB per decade, up to 16 it will continue, up to 16 it will continue. Then you are getting minus 40 dB per decade. So same graph we are obtaining over there. Let me clear my sketch. So, and the phasor plot we done over there. Okay. Now, what you have to calculate? The corner frequencies. Okay, sorry, the crossover frequencies, the gain crossover frequency. Why the gain graph is crossing 0 dB line? That is particularly this point. That is basically your gain crossover frequency, right? And you are calculating that gain crossover frequency, and with respect to the gain crossover frequency, what is basically the phase, and basically you are calculating the distance from minus 180. That is basically your phase margin, right? That means minus of minus 180 degree, whatever be the phi you are getting over there, that is basically phi at omega, what you can say, it is the gain crossover frequency omega g you are calculating. Okay. So what you find here? What you find here? It is basically phi at omega g you are calculating here, and what you get here 180 plus 140. So you are getting here near about minus 140 that will come. 180 minus 140. Okay, minus 140 plus 180. So it is near about, there is a small mistake, 40 degree positive. So positive, right? And here, what is the gain? Phase crossover frequency, it is not touching 5. So I have a minus 180 degree reference line, right? So we want to find now what is the phase crossover frequency. We are not getting there as a phase crossover frequency, so it is extended to infinite. So that's why what you can say omega p, that will be basically infinity, that percentage. And what is the respective gain? What is the respective gain? Gain graph is clearly showing it is coming towards the minus infinity. So what is the gap from the what you can say magnitude at omega equals to omega p? That you are getting minus infinity, and that reversal of that phase. So what you are getting plus infinity. Just reverse the sign. Okay, sign reversal. That was the formula, right? Because sine reversal, why? Because it is calculating the gap in between 0 degree line reference and that magnitude at omega. So we are getting that information, right? So that's why both the gain margin and the realized phase margin indicating positive, as the system is absolutely stable. You can declare as well as you have calculated the gain margin as well as phase margin. Phase margin plus minus 150 degree. Okay. Now let's move for inverse Fourier. Suppose you have given this sort of logic. So now, as your concept is clear, so you can very much easily understand. See, this is basically type 0 system, right? Type 0 system, why? Because it having no pole at origin. No pole at origin, right? It is suggesting no pole at origin. Why? Because this is the 0 dB per decade contribution. That's why no pole at origin. So it is type 0 system, right? So you have to establish from this given graph, you have to estimate, you have to establish the transfer function. That's the main objective. And all the corner frequencies is very easy. See, it has shown this one is the corner frequency, so it is 5 watt per second. This one is the corner frequency, and this is not corner. This one is the corner frequency, 100 watt per second. So you are getting the corner frequency, that is, oh, another corner is there, 40 watt per second. So after 5 watt per second, there is 20 dB per decade. That means there is a pole, you have estimated, right? Then after 40 degree there is minus 60 degree particle. That means there are the double pole, double pole, double pole, right? Double pole means after this pole there are two poles again, another two poles we have. Okay, first pole then another two pole. Then after 100 there is another pole. So you are calculating there is another pole. One pole, two pole, then another pole. Okay. So we have identified all the corners as well as respective. We have to identify now. We can easily go to the what is the transfer function of the system. Let's move on. Very simple. These are the corners. So that's why as it is minus 20 degree per decade, it is contributing actually 1 plus s by 5. Just process is reversing. 1 plus 0.2s. So for the second one, there's a double pole 1 plus s by 40. Okay, that is determining basically this one is double pole. Then we have a single pole again 1 plus s by 100. So just coagulate this one. What you get? What you get? Now you have to identify basically what is the gain factor. See, very simple as it is given 100 degree. So you are calculating 20 log of k that is providing 100. So what is k? 10 to the power 5 unit, right? So what you do your GS, you are just reversing that process. Okay. So k divided by first pole having first corner, second double pole having second corner frequency, third pole having third corner frequency. So like this way, you have accumulated all those poles as well as the gain factor. You are getting the transfer function as a whole of the system you can represent. Okay, and assigned is that here all the corner at all the corner you have to calculate the phase. So just take the phase expression. It's again coming to the part. What is basically phase expression? See what may be the phase expression. So it will decide. That is basically phase expression is as there is no pole at origin. So we are starting with the pole, this pole. That means tan inverse of omega. So what we are getting here? Omega by 5. That is minus. Then we have double pole. That means tan inverse of omega by 40, right? And that will contribute minus tan inverse of omega by 40, so 2. Then what we have here? Minus tan inverse of what we have? Omega by 100. So this is your expression. We will be calculating the phase for each of these two pieces. So tan inverse of first part, then plus 2 tan inverse of second part, then plus tan inverse of third part. So you are calculating in this way by using calculator easily you can calculate all those phases. Okay. So today what we analyzed, if there is a quadratic pole, quadratic nature that is given, so how to tackle it through the Bode plotting. How to get the Bode plot as well as we will come to the conclusion after calculating the GMPN, how to calculate the GMPN that we did already as well as how to conclude regarding the stability of the system that we understood. Okay, as well as if there is a inverse Bode plot. That means if there's a Bode plot already given, all the corner frequency mentioned, and as well as the open loop gain factor in the form in the terms of dB mentioned. So you can easily calculate here as well as all the corners. You can estimate the as a whole expression you can find out for GS. That means the transfer function of the system. Okay, so very much important for your exam also. So my next lecture will be on it. Basically, and there are two chapters left. Okay, so one will be your using the polar plot. We will be estimating. Will be again there's a graphical approach, some graphical better to say, and that approach is nothing but the Nyquist criteria. Okay, so, that will be clarified in my next class. So thank you for today.